The biggest mysteries come in the smallest packages. Today, we're tackling a math problem that sounds like a kid's game, but it has stumped the world's best mathematicians for decades. So, what is this puzzle? It's called the Collatz Conjecture. And when I say it's simple, I mean really simple. You can explain the whole thing in just 2 little steps. Yep, that's it. That's the whole game. Now, here's the crazy part, the conjecture itself. The idea is that no matter what positive number you start with, any of them, you will always, eventually, end up at 1. All right, let's give it a whirl. We'll start with something easy, like the number 6. First rule, is it even or odd? Well, 6 is even, so we just divide it by 2. Boom, we get 3.
Okay, so now we have 3, and 3 is obviously odd, so we hit it with rule 2. Multiply by 3, add 1. So 3 times 3 is 9, plus 1 is 10. Easy.
And from 10, it's just a cascade, right? 10 is even, so half of that is 5. 5 is odd, so 3 times 5 plus 1 gets us to 16. And from there, it just tumbles down. 16 to 8, 8 to 4, 4 to 2, and finally, bam, it lands on 1. See? Just like it's supposed to. Seems pretty straightforward.
Okay, so that was nice and neat. But what happens if we pick a different number? Something like, say, 27. Well, this is where our little game gets weird. The path from 27 doesn't just fall down nicely. Oh no.
With 27, the numbers don't fall at all. They do the exact opposite. They just explode upwards. It's like hailstones getting tossed around in a storm cloud, getting thrown higher and higher, all the way up to a staggering peak of over 9,000.
I mean, the path is just nuts. It's completely chaotic, totally unpredictable. It takes a whopping 111 steps, bouncing all over the place, before it finally gives up and collapses down to 1.
And it's this kind of wild behavior that led one of the greats, the legendary mathematician Paul Erdos, to basically say, look, mathematics itself, it just isn't ready for problems like this. He was saying we don't even have the right tools to think about it. So what do you do when one direction leads to total chaos? Well, you try going the other way. To get a handle on this thing, mathematicians literally flipped the problem on its head. Instead of watching these numbers fall down to 1, they asked, what if we build the structure up from 1? And how do you do that? With something called an inverse function. We're looking for the numbers that came before. So for any number n, one of its parents, so to speak, could be just 2n. But here's the tricky part. There's a second rule. If you take a number, subtract 1, and the result is divisible by 3, then that result is also a parent. It's how we find the branches. Now this is the really cool part. When you start at 1 and start applying these backwards rules, something incredible starts to happen. All of that chaos we saw before, it starts to disappear. And this beautiful hidden structure starts to emerge. Let's actually trace it out. So starting from 1, what number leads to 1? Well, only 2 works. And what leads to 2? Just 4. Okay, so far, it's just a straight line. But what leads to 4? Well, 8 does, obviously. But wait, check rule 2 for the number 4. Is 4 minus 1 divisible by 3? Yep, it is. So that means 1 is also a predecessor. And there it is, our very first branch in the tree. And as you keep going, this isn't just a branch. It becomes a vast, orderly tree. It completely reframes the whole question. The conjecture isn't just about all numbers falling down to 1. It's about whether every single positive integer has its own unique spot on this single infinite tree that grows up from 1. So this tree is beautiful. It seems to tame the chaos, but it doesn't actually solve the problem. It doesn't get us any closer to a proof. So why? What is the fundamental conflict that makes this so impossible to crack? Well, the culprit, it turns out, is a deep, ancient grudge match at the very heart of mathematics, something that number theorists talk about all the time. Okay, stick with me here. This is the core of the problem. Multiplication is orderly. We understand it. We know how it relates to prime factors. But addition, it's chaos. Seriously, just look at this table. You take a number, any number, and you just add 1 to it. That's it. And the prime factors get completely scrambled in a way that we have absolutely no way to predict. And what is the Collatz Conjecture's odd rule? 3n plus 1. It's a perfect storm. It mixes structured multiplication with chaotic addition, and that is where all the unpredictability comes from. So, even with this massive roadblock, we haven't just thrown up our hands. We've thrown computers at it. The conjecture has been checked and verified for a truly mind-boggling number of integers. That number you see there, that's more than 200 quadrillion. And in all of that testing, not one single number has failed the test. But, and this is a big but in math, checking a lot of numbers isn't the same as a proof. So after all this time, the case is still wide open. To finally put this thing to bed, a mathematician has to prove without a doubt that two things are impossible. One, that no number can just fly off to infinity and never come down. And two, that no other loop besides that little 421 we saw can possibly exist anywhere. Which leaves us with this final massive question, the one that keeps mathematicians staring at the ceiling at 3 a.m. Is the Collatz conjecture a peek into some deep fundamental truth about how numbers are structured, a hidden rule of the universe? Or is it just a beautiful cosmic coincidence that we just haven't been clever enough to break yet?